Good morning, students. We'll continue our topic as we have done about the metallurgy processes. What do you mean by metallurgy, students? The metallurgy means the extraction of metal into its pure form. That is called metallurgy. So we have done that. What are the steps which are being involved in the metallurgical process? The first one we have done, students, that is that is crushing and grinding we have done, because we get the our ores from earth crust in a combined state as well as in a native state, right, students? So to convert them into a pure metal, the following steps occurs. The first one is a crushing and grinding, the second is a concentration, and the third one is a reduction. Now today we'll do the reduction part, that how reduction of the following ores take place. As I have told you before also, that we have to reduce or to convert the metal into its pure form by looking into the reactivity series of the metals, right? The C steps involved in the extraction of metals from their ore, concentration of ore. After concentration of ore, how we can get? We have three types of metals: metals with a low reactivity, metals with a high reactivity, and metals with a medium reactivity. Students, please understand this chart very much. It's very important to be understand that how it is being carried out. Now first of all, I'll talk about the metals with a lower reactivity. If metal is present in a lower reactivity, basically it is present in the form of sulfide ores, right? Low reactivity metals means silver, gold, platinum generally occurs in a free native state. It means they can be isolated easily. But metals like copper, mercury, they are comparatively more reactive and occurs in a combined state, right? So examples are copper and mercury. So for example, the ore of mercury is cinnabar, while the copper is copper glans. So both can be converted into metallic form by using the process known as roasting, because basically this mercury or basically this copper is being present in the form of its sulfide ore. It means sulfur is being attached with it. So we find a sulfide ore of having the metals having low reactivity. So what process will apply? Will apply a roasting process. And student, what do you mean by roasting? Roasting is a process in which we heat the ore below its melting point in the excess of oxygen, right? And after roasting we'll get a metal, but this metal is not 100% purified. It required a purification step. Till here we got a 90% purity, but still for 10% we'll use our technique that is called refining or purification. Similarly, for the high reactivity, students, these are too much high. The elements, the metals are very high in reactivity, such as which metals are very high in reactivity? As you know, sodium, potassium, these are of high reactivity elements, right? Calcium, magnesium, and they cannot be obtained from their compounds by these method like roasting and calcination. I'll tell you about the calcination also. So these can be converted. Their oxide cannot be reduced with the help of carbon even. Therefore, they have a strong reducing. They themselves behave as a strong reducing agent, students. And this can be, we use only a one method, that is called electrolysis method or electrolytic reduction method for this. And after using this electrolytic reduction method, our metal is we'll get a pure metal, right? For example, sodium is isolated from sodium chloride. For example, aluminium is isolated by the electrolysis of molten aluminium oxide. I'll take one by one these all the steps. I'm just explaining you this chart, that how we can reduce it, how we can get a metal of low reactivity in its pure form, high reactivity in its pure form, and those who are having high reactivity, and the metals those who are in a medium reactivity. We know, students, the metals which are in medium reactivity, those are iron, zinc, lead. So These can be converted into their oxide by two methods, maybe by roasting or by calcination. If their ores are present in a sulfide form, right? They are treated with roasting process. And if their ore are carbonate ores, they are present in the form of carbonate ores, they are treated with the help of a process known as calcination. And this both calcination and roasting process comes under smelting. So what is smelting, students? Sorry. Smelting is a process in which crude metal is being converted into its oxide, right? Either by roasting or either by calcination. And after this, both the processes, suppose if roasting is there or if it is being carried out by calcination, the oxide of metal is being reduced to metal, reduction of metal occurs, and then purification occurs. Right, students? This is very important to be understand, because in low reactivity directly roasting occurs, then metal comes, and then metals is being refined. But in medium reactivity, first of all, while roasting or while calcination, after this process, only the metal has been converted into oxide. But one more step is being involved in the medium reactivity elements, that is reduction process. And reduction is being done by reducing agents. And these agents are carbon and carbon monoxide. And after that, only the purification step occurs. I'll take one by one. See, metals of low reactivity. Most metals are found naturally in rocks called ores, and they are in compounds chemically bonded. It means some of them are in combined form and some are in their native forms. The examples of metals having the low reactivity and present in a native form, that is uh, as well as the native form as well as the combined form, that is gold, copper, silver, platinum, mercury, right? So how the extraction occurs? Mostly low reactive elements are found as a sulfide ores. So first, these ores are roasted. After roasting, these are just heated up to reduce them from metal oxide to metals. For example, we'll take one ore of mercury, that is cinnabar. When cinnabar, the formula is HDS. First of all, we'll apply a roasting process. Roasting means the heating up of ore in the excess of oxygen. So after heating in the excess of oxygen, HDS converted into HGO. It means it form a oxide, right? And sulfur dioxide is being reduced. So after being converted into oxide, it is just heated to convert into metal. So HGO, when heated, it converted into metal plus oxygen. After this is refining process, a simple refining process which we'll deal at the last of our lecture, that is common, right? Now, extraction of middle reactivity, right? Metals, those are present in the middle of the reactivity series, such as zinc, lead, and iron, manganese. They are quite reactive and exist in nature as oxides, sulfides, and carbonates. Basically, we'll deal with the sulfides and carbonates. Those who are present in the form of sulfide, they will be treated with the help of roasting, and those who are present in the form of uh, carbonates, they are treated with the help of calcination. Calcination means absence of oxygen, right? So these metals are extracted from their ore by first converted ores to oxide, and then by the reduction. This step is very important, students. Reduction of these oxides by a reducing agents known as carbon or carbon monoxide. So first of all, I'll tell you about these two processes. First is roasting and then other is calcination. So roasting is a process to convert the metal ore, basically the sulfide ore, into the oxide in excess of oxygen. For example, zinc is present in the form of zinc sulfide. When it is treated with the excess of oxygen, it changes into zinc oxide plus sulfur dioxide. Similarly, calcination. Calcination is a process of converting the carbonate ores into oxide in the absence or a limiting supply of oxygen, we can say. So calcination involves a strong heating of ore in the absence of air, will not provide the extra oxygen to it. Only that much oxygen is present in the furnace, which is essential for the combustion, right? For example, suppose zinc is present in the form of zinc carbonate, right? Calamine ore. It is being treated with the help of a calcination process, it converted into zinc oxide and carbon dioxide. After converted into oxide, after obtaining these metal oxides, reduction steps occur. And reduction of these metal oxide is done to obtain the pure metal. Mostly carbon in the form of coke is being used for these metals. Some of them for the higher oxides, which are present relatively higher in the reactivity series, such as manganese, cannot be reduced with the coke. To reduce them, these type of oxides, right, more reactive metals than the manganese, such as sodium, calcium, and aluminium, are used. And for example, iron is also very reactive metal and cannot be reduced using carbon. For these, we use the different reducing agents, right? For example, first of all, I'll take the example like for the sulfide and carbonates, roasting is being applied, right? And for that, when the roasting and calcination is being occurred, the metal has been changes into oxide. Metal ore has been changed into oxide. It is being treated with the carbon because here carbon is acting as a reducing agent. And oxide, when reacts with carbon, it changes into pure metal. But this is for those ores, those who are present in a sulfide form and the carbonate form. But I have already explained here, students, some of the metal oxides are very, very, very reactive in nature, such as manganese cannot be reduced with coke, right? For this, what we apply, for this, we'll use a special type of reducing agents. For example, for manganese dioxide, we'll use a aluminium, not the carbon, as a reducing agent. And this type of reaction, when manganese dioxide reduces with aluminium, right here aluminium is acting as a reducing agent, reacts with aluminium, it forms manganese plus aluminium oxide, right, students? And this type of reaction is known as thermite reaction, which is very, very, very important in nature, right? Similarly, iron oxide, when reacted with aluminium, it form iron plus aluminium oxide plus heat. And this reaction is highly exothermic. The heat evolved is so large, and the metals are produced in the molten form. This reaction is known as thermite reaction, the above reaction, and it is used to fill or to join the railway tracks or cracked railway parts, machine parts of railways. Right, students? It means basically for the welding purpose it is being used, right? So this reaction is very important to keep in mind. Next is extracting the metal towards the top of reactivity series. Now metals which are present at the top of the series, such as sodium, potassium, calcium, manganese, and aluminium, they are highly reactive. And these metal cannot be reduced using coke, as I have already explained this thing. And because the affinity for the oxygen is much more than that of carbon, therefore these metals are reduced by passing an electric current through their molten salts, and this process is known as electrolytic reduction. See, students, for example, sodium is extracted from the sodium chloride. As I have already discussed this point, now how this occurs. To extract the metal, electrolytic reduction of molten sodium chloride is carried out. When electric current is passed, sodium ions, while having the positive charge, moves towards the cathode and get deposited over it after accepting the electrons. And the chloride ions have negative charge and moves towards the anode and loses their extra electron and escape out of the solution of the chlorine gas. So at cathode, students, at cathode always reduction occurs, and at anode always oxidation occurs. So first of all, loss of electron will occur at anode, and out of sodium chloride, out of sodium ions and Cl negative ions, Cl negative ions have extra charge, it will lose electrons from it in the solution, and these electrons are being carried out by the sodium ions which are at the cathode rod. It will accept the electrons and get deposited on the cathode electrode. So at cathode we'll get a sodium metal, and at anode Cl2 gas. Another example, you can see the diagram. Like for the extraction of metal by electrolysis of aluminium, the same process at cathode we're getting aluminium metal, and at anode we are getting oxygen. You can see that, right? Here again we have used the electrolytic technique, which is known as electrolytic reduction method. Now the last, when the metal has been converted into oxide after reduction, right? The metal is converted into, the metal oxide is being converted into metal after reduction, but it is not pure. So for that we use one technique that is called purification of metal. Purification of metal means the metals are not in pure form and associated with certain impurities, so that is called crude metal. So the refining or purification means the conversion of crude metal into pure metal is known as refining, and most common method is electrorefining. And this method is commonly used for the purification of metals like copper, silver, zinc, and nickel. For example, electrolytic refining of crude copper. In this, the impure metal is made as anode and the pure metal act as a cathode. And these are connected through a battery, right students, in an external circuit, and the electrolyte is used for this process. Electrolyte is that substance in which electricity is passed. When electricity is passed, it converted into ions. So ionic condition is very important for this process. So electrolyte here used as a copper sulfate itself, containing a small amount of sulfuric acid. So when the current pass, the following changes occurs. First of all, at anode, as I've already explained you, at anode, oxidation occurs, means loss of electrons. So first of all, copper, that impure metal which is present at anode, loses the electron from it and converted into copper ions, plus 2 electrons. And these electrons are being in solution. Now, at cathode, what happened? Pure metal is being there, which is acting as a cathode. So copper 2 positive ions. These copper 2 positive ions are from where it comes from the copper sulfate solution, right? Because when the current start, first of all the electrolyte breakdown, students. So electrolyte here is copper sulfate. When electricity is passed, it converted into copper 2 positive plus SO4 2 negative. So this copper 2 positive ions pick up the electrons from the solution and get converted into copper, which is being deposited on cathode, and will get a pure metal. And this technique is very important, students. See the diagram here. I have taken anode and cathode and connected to battery, positive pole and negative pole, right? Impure copper is being at anode and pure copper is at cathode, right? Now what happened? At anode, copper loses its electron, and here I have taken the electrolyte, that is copper sulfate solution. So copper sulfate solution first of all converted into copper ions plus SO4 negative ions, SO4 2 negative ions. So what happened? These ions are being in the solutions, moving in the solutions. At anode, when copper loses 2 electrons, it converted into copper 2 positive ions, and electrons are being carried out with the help of a wire, right? Through this wire, it will be in the solution. It will move towards that side. But what happened here? Basically, it happens. But what happened here? The copper ions from the copper sulfate solution, they will pick the electrons which is moving in the solution and convert it into copper metal and get deposited on the cathode. And the as the passage of time, the impurities loses as a एनोड मर्ड. यू कैन सी द इम्प्योरिटीज. एनोड के नीचे जो है इम्प्योरिटीज एज अ एनोड मर्ड जो है वो डिपॉजिट होनी शुरू हो जाती है, और एनोड धीरे धीरे डिस्ट्रॉय होना शुरू हो जाता है, और कैथोड पे प्योर मेटल डिपॉजिट होना शुरू हो जाता है. So this is very important technique. I hope you have understood. If you have any doubt, you can ask me in your doubt session. Thank you very much, students.